Hello, welcome to a video about cyclotrons. I've got a photo here of the lads with the cyclotron. I'm not sure if this was a photo that was always in colour, it might have been doctored. Cyclotrons are particle accelerators. So cyclotrons are used to accelerate ions to high speed. In stage 2 physics, you'll be expected to know that in a cyclotron, the electric field in the gap between the Ds increases the speed of the charged particles. You'll need to be able to describe how an electric field between the Ds can transfer energy to an ion passing between them. You need to be able to describe how ions could be accelerated to high energies if they could be made to move across an electric field repeatedly. You'll also need to be able to calculate the energy transferred to an ion each time it passes between the Ds, and you'll have to explain why ions do not gain kinetic energy when inside the Ds. So for some of those terms, we'll explain what they are in this video, so no stress if you're not already across what they are. So as I've already said a couple of times, cyclotrons are particle accelerators and they use electric fields to accelerate ions. They have applications in nuclear research as well as radioisotope production, and this is for nuclear medicine. I've just nicked the diagram from the workbook and used it here, and this is kind of the level of detail for electric fields that you're expected to know this in. We actually do come back to this later on when we look at magnetic fields. I'm going to play a video now first, just because I think it will give you a more complete understanding of how cyclotrons work, and then we'll go into the nitty-gritty of all of the components that we need to know so far. Whoops.
Located on the University of Saskatchewan campus and operated by the Sylvia Fedoruk Canadian Centre for Nuclear Innovation, the Saskatchewan Centre for Cyclotron Sciences builds upon the province's pioneering research in nuclear medicine and complements the university's existing suite of imaging tools. The cyclotron produces radioisotopes for medical and biological research and for use in Saskatchewan's first PET-CT scanner, located at nearby Royal University Hospital. Radioisotopes are radioactive substances created by converting a stable element into an unstable or radioactive element that can be safely used to detect and diagnose disease at a cellular level. Here is how it's done. A negatively charged hydrogen ion is injected into the vacuum chamber of the cyclotron, where two D-shaped plates are enclosed between the poles of a powerful electromagnet. An alternating positive and negative voltage between the Ds attracts and repels the ion in a circular path from one D to the other. The ion gets a boost in energy every time it crosses the gap between the Ds, causing it to accelerate. The magnetic field holds the ion within a horizontal plane, causing the ion to spiral toward the outside of the cyclotron as it accelerates. When the ion hits the extraction foil, it is stripped of its electrons, leaving a positively charged proton that then travels down a beamline toward a target. When the high-energy proton collides with the nucleus of an atom in the target, a nuclear reaction changes the atom's structure, creating a radioisotope. The radioisotope is then added to a molecule, in this case, a sugar molecule, making a radiopharmaceutical that can easily be absorbed by the human body.
So this is a diagram, an in-depth diagram illustrating that whole process. You don't need to know this too in-depth just yet. I just thought I'd show you it to put it, I guess, have it as a schematic. So the ion is injected and it travels around this circular or kind of circular path until it's accelerated out of this exit here towards a target. This is a plan view here. If you were to cut this in half and look at it on its side, this would be the view that you would have. So we've got the magnets here and here, north and south, and the magnetic field going horizontally across, and then the electric field is going vertically. That's more in depth that you need to know for the moment. I just thought I'd include that for completion. So we'll just quickly run through the components. The Ds are two semicircular hollow cavities, so here and here. The gap, which is from here to here, separates the Ds, and this contains a uniform electric field. The ion source here is where the ions enter the cyclotron, and they're accelerated in the direction of the oppositely charged terminal at the opening of the D, and obviously it'll just be one D at a time that is oppositely charged, and that will alternate, which we'll look at in a sec. The uniform electric field does work on the ions, on ions as they cross the gap, and this increases their velocity and therefore their kinetic energy. The magnetic field acts across the Ds, and this isn't shown in the diagram here. This steers the ions back towards the electric field, and it keeps them in that horizontal plane. The kinetic energy is constant inside the Ds as they are hollow conductors. If we remember back to a previous video, if a conductor is hollow, there is no charge inside that conductor, so the kinetic energy is going to remain constant. The alternating potential difference, which is indicated by this symbol here, this repeatedly changes the polarities of the D openings, and this is so the ions continue to get attracted back and forth across the gap, gradually spiraling all the way outwards until they exit and head towards their target. As they're repeatedly crossing the electric field, their velocity continues increasing, and therefore as does their kinetic energy, before exiting the cyclotron to collide with their target.